Here we can discuss few of the Java code level systems. TINI, or the Tiny Internet Interface, from Dulles Semiconductor Maxim. The TINI specification developed by Dulles Semiconductor, now Maxim, aims to bring a network connection along with high-level control and monitoring capabilities to devices ranging from industrial processing equipment to consumer appliances. The TINI interface comes in small, low-power package yet implements a complete TCP/IP node and an embedded Java server. The TINI reference specification consists of JVM running in a microcontroller and providing Ethernet and serial communications, all in a 72-pin SIMM package. Memory includes EEPROM for the operating system and other critical system code and static RAM with optional battery backup to hold programs and the JVM heap. Peripheral can also be mapped into memory space. The TINI card plugs into a second port such as Eurocard E10 that provides the connectors for serial and Ethernet communications. By embedding Java and network connection in a remote device with the TINI system, it opens up a wide range of new capabilities. SNAP, Simple Network Application Platform, from IMSIS. The SNAP card from IMSIS in Sweden comes as a TINI compatible SIMM card, but instead of a conventional microcontroller running a JVM, it uses the company's CJIP Java hardware processor. This provides for significant improvement in processing speed. The board provides expanded capabilities compared to the TINI reference system. It holds 2 MB of flash memory and 8 MB of DRAM. The system allows for the complete J2ME CLDC configuration. AJPC104 Single Board Computer from Agile Systems. The AJPC104 board from Agile Systems follows the popular PC104 format and includes the company's AJ100 have a Java processor. It can act as a standalone Java computer or fit into a PC104 stack. The company also provides an evaluation board AJ100EVB J-Stick from Sixtronics. This board also uses the 32-bit AJ100 processor from Agile System. It holds up to 8 MB of memory accessible via 32-bit wide bus. A JSIMM expansion bus provides for connection to other Sixtronics Java boards. JSTAMP from Sixtronics. This board comes as a 24-pin DIP module similar to the Javelin stamp and basic stamp modules, but uses the Agile System AJ80 chip instead. The processor provides for the full J2ME CLDC compatibility rather than a subset of bytecode instruction as with the Javelin. Java chips. Here we list some hardware Java processors that come in chip packages. Some of these chips need ancillary hardware such as power supplies, memory and so forth, but are basically complete microprocessors. They implement Java bytecode instruction instead of conventional processor type instructions. Other Java chips work as a core processor that assists a conventional processor to speed up the running of the Java program. AJ100, AJ80 from Agile. The 32-bit AJ100 derives from the JEMTM Java processor first developed at Rockwell Collins. It executes the full bytecode instruction set, including floating point with extended bytecode for I/O and threading operations. It can also implement custom bytecodes for special operations. It is suitable for real-time operations and supports for RTSJ. It offers a hard real-time multi-threading kernel with synchronization and deterministic scheduling queues. The thread yield, wait, notify and monitor enter exit are implemented directly with extended bytecodes, so a RTOS is not needed to manage the threads. A thread will yield to another within 1 microsecond. CJIP processor from IMSIS. The CJIP processor provides a complete Java instruction set including floating point operations. The chip allows for reconfiguring of internal microcode and most bytecodes are implemented in microcode. Instruction sets for C, C++, and assembler are also included. Virtual peripherals perform tasks such as timers, input-output, graphics processing, and many other services. A virtual peripheral is loaded at the microcode level and allow for fast deterministic performance. J2ME in the CLDC configuration and MIDP profile is supported. Javelin Stamp Interpreter Chip from Parallax. This chip is sold separately or as a part of the Javelin Stamp, which comes as a 24-pin DIP module. The stamp is nearly complete computer system with only the need for power and serial line to begin computing. The Java interpreter is creating with the UBCOM SX48BD microcontroller chip. The chip translates Java bytecodes into the SX48 instruction and executes them. JA108 Multimedia Application Processor Nozomi. This processor comes in a standard 16-bit SRAM flash memory package and plugged into the SRAM bus. It then acts as a core processor to accelerate Java programs, particularly multimedia applications.
This is really serious stuff, and it's demo codes.
Right, and it's not trivial computation, right? Because
no.
Because I mean, this is not, if you look at the geometry of this thing, it's not like an elbow and shoulder, right? It's this weird sort of set of intersecting triangles that work together in strange ways.
Right.
And what you have to do to make a straight line is probably the hardest thing to do with this thing.
It's called the parallel. There's your picture.
Yeah.
It's called the parallel robot, and it's sort of state of the art in industrial robotics. It's a production robot. It's working all over the world, moving chocolates and croissants around at really high speeds.
Yeah, if you ever get to see one of these things in like a croissant factory, it's actually pretty amazing that the croissants survive.
I know, right?
Because
it's moving them around.
They're accelerating the croissant at 10 Gs and they don't fall apart.
Right. And one thing I'd like to point out, this controller that we built in real-time Java is running on standard stuff. It's a U40, Solaris, Java RTS 2.0, off the shelf. This has never been done before, this kind of thing.
Right. So normally when I've seen controllers for things like this, they're about the size of a refrigerator. It's mostly these architectures that are like 20 years old that they're still building.
Right.
Device drivers and system level programming in Java. Driving hardware. What exactly is a system level programming? For most developers, it means programming at the lowest level in the system, talking directly to and controlling hardware. Device drivers represent a specific type of programming at this level. Typically, they interface with both the operating system and the hardware to give application level program access to devices in some standard fashion. Most drivers have three main sections. The first one is hardware initialization. To drive the hardware means talking to it, which in turn requires direct access to it through either memory address or specific enough instructions. The second one is the interrupt handling. To set up an interrupt handler, the driver may need to talk to CPU-specific hardware. In most cases, however, interfaces with interrupt service provided by the OS. Using those services, the driver can register an interrupt handler that is invoked or unblocked whenever the desired interrupt files. The next one is the client interfacing. Interfacing with the clients is the trickiest part and varies from system to system. On many systems, the client has to make system calls to the kernel requesting to interact with the specific device. Thankfully, that is the only way to interact with the client. Before exploring these three areas in detail, we need to cover some key Java concepts, in particular the Java native interface or the JNI.